Hi guys, this is Mrs. Gastler, and in this video we're going to talk about conservation of angular momentum, which is a new one. And we're going to do the same thing that we've been doing by comparing this to linear motion. Okay, now in linear motion we have the conservation, which I'm going to abbreviate, of linear momentum, which I like to write as CLM, conservation of linear momentum. And now we have conservation of angular momentum, which I'm not even going to write again because I'm feeling lazy right now, which is CAM, okay? CAM. So this is the abbreviations they like to use. Remember CE for conservation of energy, et cetera, et cetera. Okay, so for the conservation of linear momentum, anytime we have some sort of interaction between two objects or a collision of some sort, then what we have is that, and I'm going to write during, to make it a complete sentence, then momentum is conserved. And we say that the change in momentum, the total momentum, is going to be zero, okay? And it turns out that that's the same thing over here. So during an interaction or a collision, the change in angular momentum, the total angular momentum, is also conserved. So the total is going to be constant. The change is going to be zero. So that means that the initial total is going to be the same as the final total, okay? Same thing over here. L initial total is going to be the same as L final total. Now remember, these are both directional quantities, right? So with our linear momentum, we have like positives and negatives, okay? So maybe putting the little arrow on here will help you remember that. And if you have two dimensions, you'd want to split it up into your x and y, and then it's conserved in both directions. Here we just have the counterclockwise and the clockwise, but we still have directional, so it's directional for both. Okay, for both. That's an R right there. Okay, it's directional for both. So there's lots of different ways that we can do this. You might see an object that is like rotating like a record player, and it's got the little, I don't know if you've seen a record player, but they used to have a little thing here that would hold a record up until it was ready and you could play this record, blah, blah, blah. And then when that one was done, when the little needle got all the way to where, I don't remember if it went in or out, but when it would get to the end, it would drop the next record down so you could play the next record. So that would be an interaction right there. So we would have some change. Well, we would have no change in the total, but there would definitely be some change happening as a result of that collision between this lower one and this upper one, okay? Because they're coming into contact and we're changing the angular speed or the rotational inertia or both, but we have to make sure that the total change is still zero, okay? Just like when we had cars running into each other. Boom, boom. Same idea, okay? But here we have spinning objects instead. So I have this lovely example that we're going to go through and talk about. So we have a diver. A diver can reduce her moment of inertia by a factor of 3.5 when changing from straight to the tuck position. So I have excellent drawing skills, and you're totally going to be able to see this. So here's a diving board, and there's a pool, okay? And she's going to jump up, and she's going to be in the tuck position and maybe flipping like this, okay? Oh, hey, that's not so bad. All right, but there's rotation there, right? Because she's like jumping and spinning, and then she'll end up straight again, right? With her arms above her head. Maybe she's facing that way, who knows? And then she goes into the water, okay? So she can change her rotational, right? So moment of inertia is exactly the same as rotational inertia. I used to think they were different, and now I know they're the same. Rotational inertia. It took me some years to come up with that one, but they're the same thing, okay? Factor of 3.5 when changing from straight to tuck. So here it's going from something, so we'll call this I1, and we'll call this I2, okay? Which one do you think is bigger? That's a great question. Do you have more rotational inertia when your particles are spread out, or more rotational inertia when your particles are close together? Well, remember that it's more resistance to the change, and you resist more when it is spread out. So this is going to be the 3.5 right here because that R is bigger. Okay, so this is the 3.5 times bigger, okay? If she makes 2.0 rotations in 1.5 seconds, that is information that we can use to get our omega. So what is this? In the tuck position. So that's telling us here 2.0 rotations in 1.5 seconds. Okay, what is her angular speed here? This is what we're looking for, okay? So what do you think? You can probably know this, right? So if you think about it, so here we're having we're reducing the rotational inertia, and we're having this speed. So if we reduce the rotational inertia to get here, what's the angular speed got to be here? Is it going to be faster or smaller? And how do you know? Well, so this omega 1, so this will be omega 2 over here. Omega 1 should be, what do you think? Smaller, bigger? It should be smaller. Okay. Again, we have to have no change. Okay. So since the rotational inertia is smaller for the tuck position, then omega must be smaller for the straight position. Okay, so now let's see if we can't show that. Okay, so we'll have we'll use this form here. So the total is what's going to stay the same. So let's go with 1 and 2. Okay. Now I'm going to use the I omega 1 and I omega 2, and then I'm going to put in some stuff that I know. So I've got rotations per second. Let's see, if I just go ahead and keep rotations per second, that's kind of going to make things a little bit easier on me. I could put this into radians. 2 rotations would be, let's see, 2 pi radians is 1 rotation, and so 2 rotations would be 4 pi radians. So I could put it in terms of radians also, and that might make my brain a little bit happier. So what I'm looking for is the omega here, and I called this 1, so this is what I'm looking for. So I'm just going to go ahead and solve for that. So that's going to be I2 over I1, and my omega 2 right there. Okay, so let's see, my I2 stays and my I1, I don't even know what those are, but I know this is, I got to write it in, okay, so let's see, let's just call this I, because I know this is 3.5 times, so I'm just going to remove the 2 there and then put an I here, because then my I's are going to cancel out. I like things that cancel out. And then my omega 2. So what I'm going to end up plugging into my calculator is omega 2 over 3.5, which is going to make it smaller, which is what I expected, right? So I'll take my 2 rotations, maybe you want to stick 4 pi in there, over 1.5 seconds, and then I'm going to divide that by 3.5. That's not very pretty math, but that's what I'm going to plug into my calculator here. Let me get my calculator. My calculator says that 2 divided by 1.5 is an ugly number, 1.3, and then I'm going to divide that by 3.5, and I get 0.38 rotations per second, okay? Which is, well, let's see, what was this begin? 2, this was 2 divided by 1.5 rotations per second was 1.3 rotations per second. There we go. So it did decrease. So it is smaller when the person is straight.